Hi Calculus students! Today we are going to learn a new integration technique to add to our tool belts. And this integration technique is called U-Sub. U-Sub right here is short for U-Substitution. So U-Substitution is a technique. And then it says, and also pattern recognition. This is more so for those of you who maybe understand U-Sub very well. So if you start getting U-Sub pretty quickly, then you can learn this pattern recognition technique that just helps you do it in a faster way. Let's do an example of taking the derivative using the chain rule. So just to kind of remind ourselves of what the chain rule is and practice that so that it makes more sense when we do the opposite steps. Okay, so here I can tell that we have chain rule, and that's because I have an outside function, which is tangent, and then I have an inside function. I actually here have two inside functions. So I'm going to make a little note of that, is that there's two inside functions. And so what this is going to mean is that I'm taking two chain rules. I'm doing the chain rule twice. Okay. So you can do this along with me. This could be a good review for you, and then just check back with the answer that I get. So I'm going to take the derivative on the outside first. That's going to be secant squared. The inside will stay the same. I'm going to start color coding. I'll change colors. So then here's my first chain rule. The derivative on the inside of an exponential is just the same thing. But then I have to take the derivative of the next inside function, which is the derivative of this function, 8x. So in blue, I just had that. There you go. So my two inside functions mean I do the chain rule twice. Okay, so there's the chain rule. And now in example 2, this is a case where it's the opposite of the chain rule, and I can tell that it is because I can see that I have many functions being multiplied by each other. And some of you might be able to solve this in your head pretty quickly and know what this is. Anyone? Anyone? Maybe if I pull down example 1 a little bit. So look at the answer we got in example 1 and look what we have here. Example 1, it's just written in a different order, but if I were to rewrite this, the 8x times e to the 4x squared times secant squared of e to the 4x squared. It's the same thing that we have down here. And so this is just, example 2 is just trying to help you recognize what a problem will look like when you have to do the opposite of the chain rule. So I can still sort of see that I have like an outer function. Here's my function on the outside, and then I have a function on the inside. And if you look at what's left over is just the derivative on the inside. Okay, so there's my derivative on the inside. And what we're going to be doing, here's kind of the premise of what U-substitution is, or what doing the opposite of the chain rule is. You can kind of think of the chain rule as you have a function with an inside function, and the derivative is kind of unpacking those boxes. So like here, we had a box inside of a box inside of a box, and when I took the derivative, I unpacked all those boxes. What we're doing with integrals is now we're packing all those boxes back up, so we're going in reverse. So all this extra stuff right here needs to get packed back into the box, okay? So for instance, this little bit right here is just the derivative of there. So we pack it back in, and that goes away. And then what's left here is the derivative of this inside. So we pack it back up and that goes away. And so what we end up just doing is taking the antiderivative of the outside. So the antiderivative of secant squared is tangent. And then the inside function just stays the same. We packed everything in there. And then we have our plus c. So what we're left over with is the original function there. If this is confusing to you, that's okay. We're going to do plenty more examples, but I recommend that you pause and read all of this. So especially if you're confused, pause me, read this, and then we are going to move on to our formal definition, which is right here. Okay. So the antidifferentiation of a composition function, or a composite function, just like we said before, if we have an outside function, an inside function, and then everything else should be the derivative of the inside. Okay, so that is basically a function that has been chain ruled, right? Outside function, inside, times the derivative on the inside. And then to go in reverse, you take the derivative of the outside function, take the integral of f. So we take the antiderivative of the outside function, and then the inside stays the same. Which is kind of what I showed you there. So this is how we can solve by pattern recognition. If this seems a little confusing to you, that is where this idea of U-substitution comes in handy. So this is just like a strategy that you can use no matter what, where you can see here in this notation here, where we can replace that inside function with just U, and it makes it a lot easier to keep track of what we're doing. So let's just look at an example of this. Okay. So here we have something that has been unpacked. So I see that we have an outside function. We have an inside function. Oops. So we have an outside function, we have an inside function, and if you look right here, this actually is the derivative of what's on the inside. So if we were to follow our definition from up here, the integral of this, the integral of this will look like that. So we see we have my outside, my inside, and then the derivative on the inside. So the antiderivative, if I'm going to just make a guess what this is using my pattern recognition, which yes, I am going to hazard a guess. If I were to make a guess here, I would just take the antiderivative of the outside function and leave the inside the same. So the antiderivative of my outside function is just a power rule. So if I have a power of 12, remember I'll leave my inside the same. The power will change to 13, and then I would have to divide by that new power. So if I have to guess, this is what I'm going to guess by pattern recognition. But now I'm going to teach you the steps of U-substitution, which is a lot more, it's a lot less of a guess, and it will work 100% of the time. So let's check using that thing called U-substitution. So the way U-substitution works is we take the inside function and we set it equal to U. Okay. And basically we're changing our variable from x to u. So instead of having this dx, I need something in terms of du. So I'm going to take the derivative of u, and so then the derivative of this side becomes 2x dx. And so all of my x's and all of my dx's are going to get replaced. Okay, so right here, I'll use blue. My u, I can see, is right here. And then my du, I'll use green, is right here, 2x dx. And so everything else that I I undid my highlighting. Everything else that's not highlighted, I took it all away, is going to get replaced. So everything that's highlighted is getting replaced right now. So I'm going to rewrite my integral. Instead of x squared plus 1, I'm going to write u to the 12th power. And then instead of 2x dx, I'm going to write du. And so now instead of taking the integral of this huge, ridiculous chain ruled thing, I'm just taking the antiderivative of u squared, u to the 12th power. So the antiderivative of u raised to the 12th power is just u to the 13th, and then divided by 13 plus c. And then I'm going to substitute my u value back in because my original problem was in terms of x. I just turned it in terms of u to make it easier to solve. And I'm going to revert back to my x's. So instead of u, I'm going to write x squared plus 1 raised to the 13th plus c. Which is the same thing. Woohoo!